What I want to do is a little bit of stage setting, tell you about two industrial applications of Scenic and Verify that we did now about 4 years ago. What reference? Now it's advanced many slides. Okay. Okay, great. So hopefully this works. All right, everything is supposed to be. All right, so good. So this is going to be a case study that we did in collaboration with Boeing as part of a DARPA program. And the reason I want to cover this is that even though it's now more than 4 years since we did this, I think it's a pretty good example of full design iteration, that is using Scenic as a representation through different steps in the design process. Okay, and that includes modeling, and then verification, testing, synthesis and retraining, and runtime assurance. Okay, so the particular example that was used in this case study is a neural network-based autonomous taxiing system that Boeing, the research, the R&D folks at Boeing developed as a challenge problem for this DARPA program. And this is now, by now, this example is quite popular. Many other papers have also used this, but I think ours was the first to use it in a case study. So what does this do? So there's the setup is that there is a plane that you can see the nose of here, and on the right wing of the plane, there's a camera mounted, and this image is taken from that camera. And then these images go into a neural network, which is just doing a perception task. And the job of the neural network is to estimate what's called the cross-track error, or the CTE, which is basically the deviation of the nose of the plane from the center line that you see here on the runway. Okay, and the goal is that the CTE estimate from the neural network is going to go into a conventional controller that will control the steering and throttle, and it must keep the plane to within 1.5 meters of the center line. Okay, so here's an example of TaxiNet doing a reasonable job keeping the nose of the plane on the runway, in spite of all of these skid marks that you see here. And I think Daniel alluded to the skid marks during our post-dinner session yesterday as well. Right? Okay, so what we did was we talked to the Boeing folks and modeled the environment of this airplane system, which is essentially various kinds of runway scenarios in Scenic. And actually, you'll see that this is using only a fraction of the full expressive power of Scenic, which at the time was sufficient for what they wanted to do. Then we specify the safety requirement, and then run falsification, which is, if you're not familiar with this, it is essentially goal-directed search for input scenarios, concrete scenarios, that will cause the system to violate its safety specification. And then once it violates safety specification, we want to do some debugging to find what the failures were due to. So do some analysis and root causing, and then use that analysis to retrain the neural network, eliminate those failures, improve its overall safety and performance. And then this process can iterate for a little bit. But one aspect of modeling with Scenic that I don't think we touched upon very much yesterday, but it's an important one, is that the Scenic program, if you're especially looking at safety critical intelligent autonomous systems, the Scenic program is essentially a way of writing down our assumptions about what we expect the world to be like. But the important thing is they are just assumptions, and we should not forget that, right? And so assumptions can fail. And in fact, for robotic and autonomous cyber-physical systems, they do fail at runtime. And so you need what is called runtime assurance to essentially deal with those departures from the assumptions made in the model. Okay, so that's the last piece. Okay, so step one, modeling with Scenic. As I told you, the Scenic model was very simple for that. So what the Boeing people told us is that what can change is the time of day when the plane actually goes down the runway, whether there are clouds in the sky, and if so, what type of clouds there are, whether there's rain and how much rain there is, and the initial position and orientation of the plane on the runway. And so you'll see that being modeled here. So the Zulu time is essentially picking the time of from random between 6 a.m. to 6 p.m., expressing that in seconds. So this over here, Daniel was also mentioning this yesterday in response to a question. This is a way of specifying essentially a joint distribution over cloud type and rain, amount of rain. And so there are these 6 cloud types, and 3 of them are rain clouds. And so for, if it's one of these, then it's possible that there's no rain. And that possibility happens with probability 2/3. And then there could be these rain clouds with an amount of rain between 0.25 and 1, and that's probability 1/3. And then there's the position of the plane on the runway, right? The plane in this case is the ego object. So you're viewing the runway from the perspective of the plane. All right. So it's in fact just a static Scenic model, right? We're not even specifying a behavior for the plane because all of that is controlled by TaxiNet. All right. This is also, by the way, an example of what somebody was talking about yesterday, which is using an external neural network to control the ego object, right? I mean, this is what we did here as well as in the next case study. All right. So next step is once we have the model, we have to write the safety property. So remember, the safety property was that the plane should stay within 1.5 meters left or right of the center line. So that's the cross-track error. And so in the notation called signal temporal logic or metric temporal logic, this is what it looks like. So what this basically means is that after sometime during an initial 10-second period, the cross-track error should come within 1.5 meters. And it should stay there henceforth. Okay, it's sort of an initial transient phase that is allowed to be up to 10 seconds. So the way falsification works is it takes that logical requirement and it transforms that in a syntax-directed way into a cost function. So I won't go into the details there, but that's the row eventually is a cost function, and then we minimize that cost function. So optimization-driven search for unsafe test cases. And if the value of the cost function is driven below 0, it corresponds to a safety violation. And in this case, so this is all running using Verify. And so out of about 4,000 simulations that Verify automatically generated, about 45% of those violated the safety property, and about 9% of those left the runway entirely. So here's an example, and you can see this if it's a little clearer. So it's early morning, low light, light rain, and you can see that TaxiNet loses the center line and proceeds to drive the plane off the runway. Okay, and that's just one of about 2,000 odd simulations that had these sorts of problems. Okay, so obviously then we want to understand what went wrong. In this case, we have many simulations that failed the safety specification. So we can do analysis on this, and in fact, Verify allows you to aggregate all of that data and basically analyze which features, we call them semantic features, of the Scenic program are correlated more with failures. And originally, we thought that it would be the skid marks on the runway or things like that. But in fact, the biggest factor ended up being sensitivity to time of day. So this plot actually shows that. So the x-axis is the time of day from 6 a.m. to 6 p.m. The y-axis is the value of that cost function, remember? So if it's negative, it means it's unsafe. If it's positive, it means it's safe. So you see that TaxiNet doesn't perform well in the early morning hours, and several of the simulations were like the ones that I just showed. And then in mid-morning, early afternoon, it does okay. Again, mid-afternoon, it dips below zero, so some unsafe behavior there, and then also in the evening. All right, so one thing in particular that was a little puzzling to us is that we thought, okay, well, if it's in the daytime, then the lighting and so forth should be good enough for TaxiNet to work correctly. So why is it not performing in the mid-afternoon? And so one advantage of doing this with Scenic is that you have a representation, right? So you can basically look at the images that were generated that led TaxiNet to perform like that. And we noticed these shadowing effects. In fact, what was happening is that if it was a cloudless sky, then you would have the shadows, and that would throw off TaxiNet. In fact, if it was very cloudy sky, the shadows wouldn't show up, and it would actually do well. So there was this kind of interesting connection between the different parameters in the Scenic program that were leading to failures. Anyway, so that's the root causing, and you can do that again using that representation. So Scenic provides that representation that allows you to do this sort of debugging of the perception component. All right, and then the next step is, once we understand what the reason for the failures are, we can do essentially Scenic guided, what we call Scenic guided retraining. So the idea here is that we can generate now a new training data that includes these sorts of situations so that TaxiNet can be retrained on this. Okay, and so here's an example of performance of original TaxiNet and retrained TaxiNet on exactly the same environment scenario. And you see the original TaxiNet is essentially driving off the runway entirely, and the retrained neural network is doing a much better job. Okay. And you can also see that quantitatively. So the blue plot here is now the median value of the cost function as a function of time of day, and you see that it's always above zero, right? So the retrained neural network performs much more safely than the original. Now, one thing to remember here is that we're only using falsification, and we're not doing full formal verification or even statistical verification. So, there's still a possibility that there could be failures, right? We're just trying to falsify the system, and if we can't falsify it, it doesn't mean they don't exist. It just means that as far as your search routines go, you're not able to find any safety violations. But still, this is a much safer neural network than the original one. Okay, and then the last piece of this is the runtime assurance. So if you do that iteration with the falsifier multiple times, then you get to a point where falsifier can't find any more failures. And you could even go one further step and do what is called statistical model checking, which is to generate an estimate of the probability of safety. That gives you some confidence, but it's with respect to that particular Scenic model. So the question here is, what happens if you have at runtime, you are in a slightly different environment that is outside the distribution of the Scenic program? So for this, we had some follow-up work that was led by my former postdoc, Hazem Torfa, on automatically extracting assumptions from the Scenic model, and then using it in a very classic approach to fault-tolerant systems called the simplex architecture. So I won't go into the details there, but simplex basically, it requires a monitor to tell it whether it can trust the neural network or it should switch to something that is safer, but maybe lower performance or doesn't handle the full specification. Okay, so here you see again the TaxiNet starting off, and over here on the right-hand side top, it says trusted environment. And so that's the monitor, right? So it is monitoring a subset of the variables of the Scenic program that it can trust, like position, orientation, and in this case, I think time of day, and maybe the weather report of the what clouds in the sky. So as it goes down the runway, over there it's hard to see, but if you squint, you'll see it's starting to drift slightly to the right, And as it turns out, there was a feature of the runway that was not present in the earlier data, and the runtime monitor kicked in and switched to another controller. Okay, so that's the runtime assurance piece. All right, so that's one example, right, of a fairly simple Scenic model. No dynamic modeling in Scenic, but we were able to do multiple things using Scenic as a common representation. All right, so let me share with you another somewhat different approach. So all of the TaxiNet stuff was done in simulation because Boeing was using this simulator called X-Plane, which is what you were seeing over there for all the experiments. Even the original training data was generated from X-Plane. But an obvious question is, if I do some analysis with Scenic and verify in simulation, how much of that carries over to the real world? Okay, and so that's the subject of a different case study that we did 4 years ago. So the questions we asked there is, number one, if you find safety violations in simulation, do these transfer over to the real world? And if so, how well? And secondly, can they actually use simulation to design the tests that we'll run in the real test bed on the road? Okay. And that's the second case study that we did in collaboration with the American Automobile Association, AAA, and LG, Silicon Valley Labs, which at the time they were designing the simulator, which many of you know of, which is now called the SVL simulator. And AAA operated and still operates this large testing facility in the Bay Area called the Momentum Station. And that's where we ran the tests. Okay, so the overall flow is we have to create a model of the test track, so the Momentum, a portion of the Momentum station, in a simulator that's LGSVL. Then we have to specify the scenario in Scenic. We specify our safety properties, and then we run the falsifier just like the Boeing case study. And once again, as you will see, the falsifier came back with lots of unsafe test cases in simulation. But the question here is, how much of those are really unsafe on the road, right? And so we go through this process of test case selection to take many test cases and whittle them down to just a handful that you can actually run on the track. Because as those of you who have actually done this know, it's very time consuming, it's expensive, and you want to run each test case multiple times because there are various other variabilities that you don't have full control of. Okay, so you get those test cases, you run them on the track, and then you get data, and then we analyze the data to understand what was going on. Okay, so the particular scenario that we designed with our collaborators was something that was a pedestrian vehicle scenario. And there's good reasons to pick these sorts of scenarios because they are pretty critical in terms of overall safety. And so here's what the scenario was. So up here on the top left, you see the vehicle that was using. It's pretty dated by now, right? So it's Lincoln MKZ running an old version of Baidu, now old version of Baidu Apollo's software. But you see there's a LiDAR on the top, and that's sort of the primary sensor that this car was using. If you look at the map on the right, that is basically the portion of the Momentum station that we were testing on. And so if you look at the blue dashed line, the dot at the bottom right is where the autonomous vehicle started on First Street, and the autonomous vehicle was basically programmed to go down First Street, make a right turn on Pearl, and then end at this top right blue dot. Now, the setup was that we had a pedestrian crash dummy that is used in crash testing in the test tracks. And this crash dummy was moving along the track that was laid here. It's sort of a pedestrian walkway. And so it starts at the yellow dot, and it has to cross the road and get to the red dot. But this particular pedestrian model, we programmed in Scenic a behavior that the pedestrian would hesitate in the middle of the road. Okay, so the pedestrian dummy moves into the middle of the road, then it randomly hesitates for a random period of time, and then decides to continue on. Okay. And so here's the snippet of the Scenic code where the Ego vehicle has a in this case, a predeterministic behavior. It just has to drive to a particular latitude, longitude location. And then the pedestrian is also just going to cross, but it has this behavior hesitate, which has these three parameters, which have random values. So the first one is start delay, which is the difference between the time that the car starts and the time when the pedestrian dummy starts, which is between 7 and 15 seconds, uniform random. Walk distance is the distance traveled by the dummy before it hesitates. So 4 to 7 meters, I think, in this case. And then hesitate time is the time the pedestrian dummy will hesitate in the middle of the road. Okay, between 1 and 3 seconds. All right, so again, Verify ran about 1,200 simulations, and 2% of those were unsafe. Unsafe in this case means that the pedestrian dummy got within a minimum distance of the car. Okay, and then what you're seeing here is a representation of all of those simulations, where the x-axis is start delay and the y-axis is walk distance, so 2 of those 3 parameters. And the color indicates whether it was safe or unsafe. So warm colors like yellow and orange are safe. Cold colors like blue and purple are unsafe. What we did in this case, actually, our goal was to kind of pick a diverse set of test cases in terms of their safe, unsafe profile, and then execute them on the track. And so we picked some that were robustly safe, meaning that there's like a yellow dot surrounded by yellow dots or orange dots. We picked one that was marginally safe, which is like something that is yellow or orange, but if you put up the parameters slightly, it becomes blue or purple, right? Unsafe. And then something that is, we call it robustly unsafe, meaning that it's like a blue or purple dot surrounded by some of those as well. Okay. And so overall, what we found was that if the simulation was safe and was unsafe in simulation, it was also majority of the time unsafe on the road, and I'll show you an example of that. And what we also found that it was safe in simulation, but the vast majority, almost always, it was safe on the road. And we can talk more about why this might be, and the paper actually has quite detailed discussion of this. But let me show you this particular example. So here you see the pedestrian dummy here on the right. The car comes down on the turn. The dummy moves into the road. And the car detects it, in fact. It stops for the pedestrian, but then decides to drive into it anyway, right? So this is an example of something that we saw in simulation, and like wondering, okay, is that actually something that will happen? And in fact, it did, right? And there were multiple more of these sorts of things that happened, both safe and unsafe. So then, in many autonomous vehicle stacks, you can actually go and replay because you have a log of what happened. And so we did this in the Baidu stack. And now what you're going to see is from Apollo's perspective, what was happening. So the car, it's showing the visualization of the car coming down there on the turn. And you see the fence, the pink fence, that's where it's supposed to stop, right? So it's coming on the turn. And now it sees the yellow box. That's the pedestrian dummy. So it sees the box, it puts a fence, it stops. And then at some point, it loses the box, yellow box, and then it runs into the pedestrian. Okay, so it does seem that there was a perception failure, probably big to begin with, but there's also a prediction failure, right? Because if you know that there's a pedestrian and suddenly it disappears, then the system shouldn't just assume that there's no pedestrian anymore. So anyway, I think like many failures, there's multiple possible reasons throughout the stack. All right, so that's another example of another case study we did. Okay, the main difference was this actually was a way of using Scenic and Verify to design real-world tests. You can do, hardware-in-the-loop testing, but you can also do road testing or real system testing with Scenic and Verify, right? And then you can also use them to understand what happened wrong, and you can use them to design the test as well. Okay, so let me quickly summarize here, and then we'll move to breakout sessions. So here's just a laundry list of some of the features of Scenic that were covered yesterday. I want to talk more about use cases today. I think today is going to be a lot about ways to use Scenic and associated tools. So synthetic data generation is one of the use cases that we started with, and I know many people in the room are also interested in this. But you can also, as we showed, use it for test generation, including fuzz testing, And if you specify requirements in a formal notation, then you can use it for formal verification, like control logic falsification or statistical model checking. We showed that we could do this, use it for debugging and triage, like in the Boeing case study. And similarly, also, you can use it for data augmentations, for generating new data and retraining. One thing I didn't talk about, but this is actually mentioned in the Verify paper, is that you can also do what we call goal-directed parameter synthesis. That is to say, if you have parameters of your machine learning model or your controller, and you want to synthesize the parameter values so as to satisfy a specification, you can do that as well. So that's something that we did in the context of RL a few years ago. Runtime model generation, I showed you an example of that. Sim to real validation, in fact, the AAA case study that I showed you is one way to do sim to real validation. In yesterday's post-dinner discussion, there was a lot of interest also in using Scenic as a language to query real data, some work that Eddie Kim has done. And that's another sim to real approach to sim to real validation. You can use it for generating training data for and on curriculum for reinforcement learning. I know somebody was interested in Scenic for RL, so that's another. And then another application also that Eddie Kim and Daniel Hay and a few others are doing is on using Scenic as a way to model worlds for extended reality, and then actually now having people in these settings and training and testing people's abilities in extended reality applications. Okay, but I think really, to be honest, when we started the Scenic project, we probably didn't have most of these bottom cases. We were just working on the ones at the very top. And so I think the number of use cases have expanded over time as more people have joined us on this project. So it would be great to hear about new applications. If you can think of them, please do share them. And that's what the rest of the day is for, right? More discussions